Hello my friends and welcome back to KrossUSA channel. Today we're taking you on an incredible journey through 7 of the most sophisticated manufacturing processes happening right now in facilities around the globe. So grab your coffee, settle in, and let's dive into the fascinating world of heavy manufacturing. Our first stop takes us to Shandong in China, where we witness the mesmerizing production of grinding balls, those unsung heroes of the mining and cement industries. Now, you might wonder why steel balls deserve our attention, but let me tell you, these aren't your average ball bearings. The process begins with carefully selected steel bars, typically made from high-carbon chromium steel with a carbon content between 0.7 to 1.2%. The magic happens in their automated forging line, where each steel bar is heated to approximately 1,100 degrees Celsius in a walking beam furnace. This temperature is crucial. Too hot and the steel becomes too soft, too cool and you'll crack your dies. Watch as the glowing steel enters the forging press, a massive 1,600-ton hydraulic beast that shapes each ball in a series of progressive dies. The first impression creates a rough sphere, while subsequent hits refine the surface and ensure perfect roundness. The precision here is remarkable. We're talking about tolerances within 0.1 millimeters on balls that range from 20 millimeters to 150 millimeters in diameter. After forging, the balls travel through a controlled cooling conveyor where they're air-cooled to about 850 degrees Celsius, then oil-quenched to achieve that perfect balance of hardness and toughness. The final hardness typically reaches 58 to 65 HRC. Now we shift gears to witness one of the most demanding manufacturing processes in the world, forging gun barrels for U.S. Army tanks. This isn't just metalworking, this is creating the backbone of America's armored superiority. The process starts with a solid steel billet, typically weighing around 2,000 pounds, and made from specialized gun steel containing chromium, molybdenum, and vanadium. This isn't your everyday steel. It's engineered to withstand pressures exceeding 60,000 psi and temperatures over 3,000 degrees Fahrenheit when firing. The heart of this operation is the rotary forging machine, a technological marvel that can apply up to 3,000 tons of force while rotating the workpiece. The billet is heated to 2,100 degrees Fahrenheit in a carefully controlled atmosphere furnace to prevent oxidation. Temperature uniformity is critical. Variations of even 50 degrees can create stress concentrations that could lead to catastrophic failure. Watch as the heated billet enters the forging press. The process uses what's called gun drilling combined with forging. First, a pilot hole is created, then expanded using a specialized boring technique that maintains perfect concentricity. The barrel is then forged from the outside while the boring tool works from within, creating that precision rifling that gives projectiles their spin and accuracy. The rifling process is particularly fascinating. Using a broaching machine with carbide cutting tools, spiral grooves are cut with tolerances measured in 10,000ths of an inch. Each groove must be perfectly uniform. Any variation affects accuracy at ranges exceeding 2 miles. Heat treatment follows forging, where the barrel undergoes a precise stress relief process at 1,150 degrees Fahrenheit for 6 hours, followed by controlled cooling. This eliminates internal stresses that could cause warping or cracking under the extreme conditions of combat. Quality control is absolutely crucial. Each barrel undergoes proof testing with charges 25% higher than service loads, dimensional inspection using coordinate measuring machines, and magnetic particle inspection to detect any microscopic flaws. The entire process, from billet to finished barrel, takes approximately 8 weeks and represents the pinnacle of metallurgical engineering. Let's journey to Bulgaria, where forging and press plant JSC Ruse creates some of the most critical components in steel production, rolling mill rolls. These massive cylinders are the workhorses that shape everything from railroad tracks to the steel beams and skyscrapers. The process begins with a forged steel ingot weighing up to 60 tons. That's equivalent to about 40 cars. The steel composition is carefully engineered with chromium, nickel, and molybdenum to achieve the perfect balance of hardness and toughness. These rolls need to maintain their shape under pressures exceeding 10,000 tons while processing steel at temperatures over 2,000 degrees Fahrenheit. The ingot starts its journey in a massive reheating furnace where it's brought to 2,300 degrees Fahrenheit. The heating process alone takes 72 hours to ensure uniform temperature throughout the entire mass. Rapid heating would create thermal stresses that could crack this valuable steel. Now comes the spectacular part, the forging operation. Using a 12,000-ton hydraulic press, one of the largest in Eastern Europe, the heated ingot is gradually shaped through a series of carefully planned reductions. Each bite removes specific amounts of material while maintaining the grain structure that gives the roll its strength. The forging process uses what's called cogging. The ingot is rotated 90 degrees between each press stroke, gradually elongating and refining the internal structure. This process breaks up the cast structure of the original ingot and creates a fine, uniform grain pattern that's essential for the roll's performance. Temperature control throughout forging is absolutely critical. Pyrometers continuously monitor the steel temperature, and if it drops below 2,000 degrees Fahrenheit, the piece must be reheated. The entire forging operation can take 8 to 12 hours for a large roll. After rough forging, the roll undergoes precision machining on a specialized heavy-duty lathe capable of handling 80-ton workpieces. The final diameter tolerance is held to within 0.02 millimeters, remarkable precision for such a massive component. Heat treatment is the final critical step. The roll is heated to 1,650 degrees Fahrenheit, then oil quenched and tempered at 1,200 degrees Fahrenheit. This creates a hard working surface with a tough, ductile core that can absorb shock loads without fracturing. Quality assurance includes ultrasonic testing of the entire volume, hardness testing at multiple depths, and dimensional verification. These rolls will operate continuously for months, processing thousands of tons of steel with minimal wear, a testament to this remarkable manufacturing process. We're now witnessing precision forging at its finest, the production of 155mm artillery shells using a massive 2,000-ton Yumuko hot forging press at the EAS Hymettus plant. This is where raw steel transforms into components that demand absolute perfection in both dimensions and metallurgical properties. The process begins with carefully selected steel billets made from high-strength, low-alloy steel containing manganese, chromium, and molybdenum. Each billet weighs approximately 45 kilograms and must meet strict chemical composition requirements. Even small variations in carbon content can affect the shell's performance characteristics. The billets are heated in a walking beam furnace to precisely 1,200 degrees Celsius. This temperature is critical. It must be hot enough for plastic deformation, but not so hot that grain growth occurs. The heating process takes 45 minutes and uses a protective atmosphere to prevent oxidation that could weaken the final product. The Yumuko press itself is an engineering marvel. With 2,000 tons of forging capacity and servo-electric drive systems, it can control force, position, and speed with incredible precision. The press operates at speeds up to 200 millimeters per second during approach, then slows to mere millimeters per second during the actual forging operation. Watch as the heated billet enters, the forging dies. The shell forging uses a 3-stage process. First, upsetting to redistribute material, then preforming to create the basic shell shape, and finally finish forging to achieve final dimensions. Each stage requires different die geometries and force applications. The die design is particularly sophisticated. Made from hot work tool steel and heat treated to 48 to 52 HRC. These dies must withstand repeated thermal shock and mechanical stress. The dies are preheated to 350 degrees Celsius to minimize thermal gradients that could cause cracking. During forging, the material flow is carefully controlled to eliminate internal voids and ensure uniform grain structure. The press's computerized control system monitors force, displacement, and timing to within milliseconds, ensuring each shell meets exact specifications. Temperature monitoring continues throughout the process using infrared pyrometers. If the workpiece temperature drops below 1050 degrees Celsius, it must be reheated to maintain proper material flow and prevent die damage. After forging, the shells undergo controlled cooling to room temperature, followed by stress relief heat treatment at 650 degrees Celsius for 2 hours. This eliminates residual stresses from the forging operation. Prepare to be amazed as we witness the complete transformation of a massive solid steel block, measuring 1,000 by 1,000 by 1,200 millimeters and weighing an incredible 6,940 kilograms, into a precision machined component at the Euro BLECH 2014 Trade Fair by Von Schaven AG. This is heavy machining at its most impressive. This isn't just any steel. We're looking at a grade 42 CRMO4 alloy steel block, heat treated to approximately 280 to 320 HB hardness. That's roughly equivalent to the hardness of a good file, making this an extremely challenging machining operation that showcases the capabilities of modern CNC equipment. The workpiece is mounted on a massive 5-axis CNC machining center, specifically designed for heavy-duty operations. The machine table can handle loads up to 20 tons and features hydraulic clamping systems that secure the workpiece with tremendous force while maintaining precision positioning within 0.01 millimeters. The spindle system is particularly impressive, a 75 kilowatts electrospindle capable of delivering 8,000 Newton meters of torque at low speeds, essential for the heavy cuts required in this operation. The spindle speed ranges from 20 to 3,000 RPM, with the slower speeds used for roughing operations and higher speeds for finishing. The machining process begins with face milling, using a 200 millimeters diameter indexable face mill with carbide inserts specifically designed for steel machining. The cutting parameters are carefully optimized: 150 meters per minute cutting speed, 0.8 millimeters rev feed rate, and 3 millimeters depth of cut. These parameters balance productivity with tool life, crucial when machining such expensive workpieces. Coolant management is critical in this operation. High-pressure coolant at 80 bars floods the cutting zone, carrying away the tremendous heat generated and flushing chips from the cut. The coolant system circulates 400 liters per minute of specialized cutting fluid that provides both cooling and lubrication. Watch as the machine executes complex 3D toolpaths, removing material layer by layer with mathematical precision. The CNC control system, a Siemens 840 DSL, calculates millions of positioning commands per second, coordinating all 5 axes simultaneously to maintain optimal cutting conditions. The roughing operations remove approximately 3,000 kilograms of material, nearly half the original weight. This generates an enormous amount of chips, which are continuously evacuated by a powerful chip conveyor system. The chips themselves are valuable, representing hundreds of dollars worth of recyclable steel. Semi-finishing operations follow, using smaller end mills and higher spindle speeds to achieve better surface finish and dimensional accuracy. The machine maintains positioning accuracy within 0.005 millimeters throughout these operations, despite the enormous cutting forces involved. The finishing passes are works of art. Using ball-end mills and optimized cutting strategies, the machine creates complex curved surfaces with surface finishes better than 1.6 micrometers raw. The final dimensional accuracy across the entire component is held within 0.02 millimeters, remarkable precision for such a large workpiece. Tool changes happen automatically through a 60-tool carousel system. Each tool is precisely measured using a laser tool setting system, ensuring perfect dimensions and runout characteristics. Tool life monitoring prevents tool breakage that could damage the expensive workpiece. Quality control throughout the process uses in-process probing systems that verify dimensions without removing the workpiece from the machine. This closed-loop feedback ensures that any dimensional variations are immediately corrected. The entire machining process takes approximately 18 hours of continuous operation, representing a masterpiece of manufacturing engineering and precision machining capabilities. Welcome to ISA CSRL, where we're witnessing the fascinating combination of stamping and precision machining that creates complex steel components used in automotive and industrial applications. This integrated approach represents the future of efficient manufacturing. The process begins with high-strength steel strip, typically 3 to 6 millimeters thick, supplied in coils weighing up to 20 tons. The steel grade varies depending on the application, from deep drawing quality for complex shapes to high-strength low-alloy steels for structural components. Each coil represents thousands of potential parts. The stamping operation uses a progressive die system in a 400-ton mechanical press. What makes this fascinating is the precision required. We're talking about forming operations that maintain tolerances within 0.1 millimeters while operating at speeds up to 60 strokes per minute. The dies themselves are works of art, machined from tool steel and hardened to 58 to 60 HRC. Watch as the steel strip feeds through the progressive die. Each station performs a specific operation, first piercing holes, then forming bends, drawing cups, and finally trimming excess material. The strip advances exactly 127 millimeters between each stroke, precision timing that's maintained by servo-driven feed systems. The forming forces are enormous. During deep drawing operations, the press applies up to 300 tons of force, while the material flows into complex shapes. Lubrication is critical here. Specialized drawing compounds reduce friction and prevent galling that could damage both the part and the expensive dies. Temperature control of the dies is crucial for consistent part quality. Cooling channels machined into the die maintain temperatures within 5 degrees Celsius of the set point, preventing thermal expansion that could affect part dimensions. The cooling system circulates temperature-controlled fluid at precise flow rates. After stamping, selected parts move to the machining stations for secondary operations. These aren't your typical machine tools, but specialized equipment designed for high-volume production. CNC lathes and machining centers with automatic part loading systems maintain cycle times under 45 seconds per part. The machining operations add precision features that can't be created during stamping, threaded holes, precision bores, and complex surface profiles. Cutting tools are specifically selected for the work-hardened stampings, typically carbide inserts with special coatings to handle the challenging material conditions. Our final stop takes us to Sweden's Kihlberg's Stall AB, where we witness the ancient art of open die forging elevated to modern precision manufacturing. This process, fundamentally unchanged for centuries, yet refined with modern technology, creates some of the highest quality steel components available today. Open die forging differs dramatically from closed die operations we've seen earlier. Instead of pressing material into shaped dies, the workpiece is gradually shaped between flat or simple curved dies, requiring tremendous skill from the operator and precise control of the forging process. The process begins with a steel ingot weighing up to 15 tons, typically made from premium alloy steels containing chromium, nickel, and molybdenum. These materials are destined for critical applications: turbine shafts, pressure vessel components, and aerospace parts where failure simply isn't an option. The forging press itself is a 6,000-ton hydraulic giant, but unlike the automated presses we've seen, this requires human artistry. The master forger, with decades of experience, reads the steel's behavior, watching for color changes, listening to the sound of the press, feeling the material's response through the controls. The forging process uses what's called drawing out. The ingot is repeatedly compressed and rotated, gradually elongating while refining the internal grain structure. Each compression is carefully calculated to maintain proper reduction ratios, typically 3:1 to 4:1, which breaks up the cast structure and eliminates internal voids. Temperature management is critical throughout the operation. If the steel temperature drops below 1,100 degrees Celsius, the piece must be reheated. Infrared pyrometers continuously monitor temperature, but the experienced forger can judge temperature by color. Bright orange indicates proper forging temperature, while dark red means reheating is needed. The grain refinement achieved through open die forging is remarkable. The original cast structure with grain sizes of 5 to 8 millimeters is reduced to 0.5 to 1 millimeter, creating a fine, uniform microstructure that provides superior mechanical properties: higher strength, better toughness, and improved fatigue resistance. The forging operation for a large shaft can take 6 to 8 hours of continuous work. The coordination between crane operators, furnace operators, and the master forger is like watching a carefully choreographed dance. Each team member knows their role in creating these magnificent components. Heat treatment follows forging, where the component undergoes normalizing at 900 degrees Celsius followed by tempering at 650 degrees Celsius. This optimizes the grain structure created during forging and achieves the final mechanical properties required for service.